section 8.7, MOSFET biasing. There are three ways to bias a MOSFET, called zero bias, voltage divider bias, and drain feedback bias. Alright, on page 405, E-MOSFET bias. Because E-MOSFETs must have a VGS greater than the threshold value, if you can recall the characteristic curve that we've just looked at, zero bias, of course, cannot be used. Underline that. Makes sense, no? If we remember the characteristic curve. So figure 846 shows two ways to bias an E-MOSFET. D-MOSFETs, of course, can also be biased using these methods. An N-channel device is used for purpose of illustration. In either the voltage divider or the drain feedback bias arrangement, the purpose is to make the gate voltage more positive than the source by an amount exceeding VGS threshold. And of course the equations, as you can see there on page 405, are familiar. If I want to determine VGS, voltage divider formula, voltage drop over R2, which is VGS, is R2 divided by R1 plus R2 times this, multiplied with the supply voltage, which is VDD. And of course, VDS, applying Kirchhoff's law again, is the supply voltage VDD minus the vol drop over RD, which is ID times RD. Where ID, of course, is K in brackets multiplied with VGS minus VGS threshold squared, as we've seen in equation 8.4. So in the drain feedback circuit in figure 846b, there is a negligible gate current and therefore no voltage drop across RG. No voltage drop across RG. This, of course, makes VGS equal to VDS. But let's have a look at the examples here at the bottom of the page. On page 405, example 818. Determine VGS and VDS for the E-MOSFET circuit in figure 847. Assume this particular MOSFET has a minimum values of ID on is 200 milliamps at the VGS of 4 volts and VGS threshold is equal to 2 volts. Alright, then for the E-MOSFET in figure 847, the gate to source voltage using the voltage divider formula, R2 over R1 plus R2 times VDD, gives me a value of 3,13 volts. To determine VDS, I first have to find K, of course, using equation 8.4 as we've seen. And of course using the minimum values that's been given, ID on and the specified specified voltage values. So K then, ID on divided by VGS minus VGS threshold squared, get an answer of 50 milliamps per square voltage. Now calculate ID, same as we've done in the previous example. ID is equal to then the normal formula, K brackets VGS minus VGS threshold squared, get an answer of 63.8 milliamps. And then finally, calculate VDS using Kirchhoff's law, is VDD minus IDRD. Just calculated ID, and I get a value of 11.2. Right, example 819. Determine the amount of drain current in figure 848. The MOSFET has a VGS threshold of 3 volts. Now if I go and look at figure 848, I can see that the meter indicates that VGS is equal to 8.5 volts. So since this is the drain feedback configuration, VDS is equal to VGS, if you recall, because there's negligible current flowing. So I can just calculate ID, which is VDD minus VDS over RD, and it gives me an answer of 1.38 milliamps, straightforward. Alright, that's the E-MOSFET bias. Let's have a look at the D-MOSFET bias at the bottom of page 406. Recall that the DMOSFETs can be operated with either positive or negative values of VGS. Ne? A simple bias method is to set VGS is equal to 0 so that an AC signal at the gate varies the gate to source voltage above and below the 0 volt bias point. A MOSFET with a 0 bias is shown in figure 849A. Since VGS is equal to 0, ID is equal to IDSS as indicated. No? We can all see that in figure 849. The drain to source voltage then of course is expressed as follows using Kirchhoff's law again. VDS is equal to VDD minus IDSS times RD. Remember we've said that ID is equal to IDSS. Again here the purpose of RG, as we've seen in previous section as well, is to accommodate an AC signal input by isolating it from ground as shown in figure 849b. Since there is no DC gate, current RG does not affect the 0 gate to source voltage. Ne? But let's have a look at the example, example 820. It says there, determine the drain to source voltage in the circuit of figure 850. The MOSFET datasheet gives VGS off is equal to minus 8 volts and IDSS is equal to 12 milliamps. Now we know since ID is equal to IDSS, which in this case is 12 milliamps, the drain to source voltage, Kirchhoff's law, VDD minus IDSS times RD, gives me a value of 10.6 volts. Straightforward. Alright, so that is then for the D MOSFET bias. Alright, this concludes then section 8.7, which is concerned with MOSFET biasing.